Somewhere off the coast of the Pacific Northwest, deep beneath the ocean floor, an invisible force has been building for more than 3 centuries. Scientists warn that sometime within the next 50 years, it could unleash a magnitude 9 earthquake, one of the most powerful natural events the modern world has ever witnessed. When it happens, stretches of coastline will sink by 2 meters in a matter of seconds. The ground will shake without mercy. And minutes later, a wall of ocean water will come roaring inland, wiping entire towns off the map before most residents even understand what hit them. The source of all this hidden danger is a massive fault line buried under the Pacific Ocean called the Cascadia subduction zone. This dormant giant has the power to upend the lives of nearly 13 million people almost instantly. History tells us it has done this before, and the geological evidence building up today suggests it is preparing to do it again. Right now, an international team of researchers is watching this fault line breathe in real time, using some of the most advanced monitoring technology ever deployed, all in an urgent race to figure out exactly when the next disaster will strike. Today, we're diving into how scientists are trying to predict the next Cascadia megaquake. Because for the millions of people living along this coastline, this isn't really a question of whether it will happen. It's a question of when. Beneath the calm, scenic coastline of the American Pacific Northwest sits one of the most dangerous geological structures on the planet, known to scientists as the Cascadia subduction zone, or simply the CSZ. Stretching more than 1,000 kilometers from Northern California all the way up to Vancouver Island, this is the boundary where the Juan de Fuca plate is being forced, slowly and relentlessly, underneath the much larger North American plate. When a fault line like this finally gives way, it doesn't produce an ordinary earthquake. It produces what geologists call a megathrust earthquake, capable of reaching magnitude 9 or higher on the Richter scale. Because the Richter scale is logarithmic, each single whole number increase represents roughly 10 times more ground movement and about 31 times more released energy. A magnitude 9 event sits near the absolute upper limit of what our planet is capable of producing. These earthquakes are so rare that entire human generations can pass without anyone alive experiencing one. Yet, when one finally arrives, it permanently rewrites the region it strikes. To put the scale of that power into perspective, a single magnitude 9 earthquake can release energy roughly equal to 2 million Hiroshima-sized atomic bombs, or about 31 billion tons of TNT, all detonating beneath your feet in the span of a few violent minutes. To understand where all this destructive power comes from, we need to zoom out and look at the bigger picture surrounding the entire Pacific Ocean, a region geologists call the Ring of Fire. This horseshoe-shaped belt stretches more than 40,000 kilometers and contains over 450 active volcanoes and earthquake hotspots, many hidden beneath the waves. Roughly 90% of all the seismic activity on Earth, and about 3/4 of its active volcanoes, are concentrated along this single ring. The Ring of Fire exists because of the constant, restless motion of Earth's tectonic plates, colossal slabs of crust and upper mantle, some as wide as entire continents and up to 200 kilometers thick, floating atop a hot, semi-molten layer called the asthenosphere. Heat rising from deep within the planet's interior drives this motion, causing plates to collide, separate, or grind past each other, generating tremendous mechanical stress along their boundaries. In the Cascadia region specifically, we find what's called a convergent boundary, where the dense oceanic Juan de Fuca plate is sliding beneath the lighter continental North American plate at a pace of roughly 4 centimeters per year, about as fast as your fingernails grow. In certain stretches, this movement happens gradually through what scientists call slow slip events, sometimes nicknamed silent earthquakes, releasing small amounts of energy gradually over weeks or months, often accompanied by faint tremors, too subtle for humans to feel but easily picked up by sensitive seismic instruments. But this sliding motion is never perfectly smooth everywhere along the fault. In sections where the plates lock together, stress accumulates steadily over decades or centuries until it finally reaches a breaking point. The plates lurch violently past one another, unleashing all that stored energy at once in the form of a devastating megathrust earthquake. The most recent example of this kind of event struck off Russia's Kamchatka Peninsula on July 29, 2025, registering a massive 8.8 in magnitude at a depth of 35 kilometers. Scientists warn that when, not if, a similarly powerful rupture eventually strikes the Cascadia zone, the Pacific Northwest could face one of the most destructive natural disasters in the entire history of North America. Current predictions suggest the ground near the coast would shake violently for roughly 3 minutes straight. Sections of coastline would drop by around 2 meters almost instantly. And because the rupture happens underwater, it would almost certainly trigger a tsunami, potentially a wall of seawater as tall as 30 meters, stretching along more than 1,000 kilometers of coastline, destroying virtually everything in its path as it surges inland. As alarming as that scenario sounds on its own, a study published in the journal Geosphere on September 29, 2025, revealed something even more unsettling. Marine geologist Chris Goldfinger and his research team found evidence suggesting that the Cascadia subduction zone might not be acting entirely alone. According to their findings, it may actually share a hidden connection with another one of the most dangerous fault systems on the west coast, the San Andreas Fault. The San Andreas is already one of the most active fault lines on Earth, responsible for more than 10,000 earthquakes every year across Southern California, and it runs as close as 56 kilometers from downtown Los Angeles. For decades, scientists have theorized that major fault systems could somehow influence each other's timing, but concrete, real-world evidence supporting that idea has always been difficult to come by. That changed thanks to a discovery that began almost by accident back in 1999. During a research expedition off the coast of Oregon and Northern California, Goldfinger's team was collecting sediment cores that recorded roughly 300 years of geological history along the Cascadia Fault. These cores contained layers called turbidites, essentially fingerprints left behind by underwater landslides frequently triggered by large earthquakes. At one point during the expedition, the ship drifted slightly off course, ending up about 88 kilometers south of the San Andreas Fault Zone. Rather than ignore the detour, the team decided to collect a few additional sediment samples while they were there. What they eventually found in those samples was startling. The turbidite layers collected near the San Andreas closely matched the timing and structure of layers from the Cascadia Zone hundreds of kilometers away, hinting that both fault systems may have ruptured within hours or even minutes of one another on more than one occasion throughout history. The implications of this are genuinely alarming. It suggests that the next major Cascadia rupture, the event some articles have started calling the Big One, might not strike in isolation. It could potentially coincide with a major rupture along the San Andreas as well, creating a compound, cascading disaster across the entire west coast simultaneously, putting cities like Seattle, Portland, San Francisco, and Vancouver all at risk within the same catastrophic window, a scenario that could cost thousands of lives and tens of billions of dollars in damage. With a threat this serious, the obvious question becomes, when did the last one actually happen, and can we use that to predict the next one? To answer that, scientists first had to look backward, piecing together clues from indigenous oral history, dead forests, and even foreign shipping records from the other side of the world. Long before modern seismographs existed, indigenous communities along the Pacific Northwest coast passed down vivid oral histories describing catastrophic ground shaking and enormous waves. On Vancouver Island, the Nuu-chah-nulth people tell stories of mountain dwarves who invited villagers to dance around a great drum, warning that if the drum was ever accidentally struck, the dancer would develop what they called earthquake foot, each step causing the ground to shake and the ocean to surge ashore with almost no warning at all. Remarkably, this wasn't an isolated legend. A research team led by Ruth Ludwin at the University of Washington, made up of anthropologists, geologists, and indigenous scholars, examined roughly 40 separate oral traditions from coastal groups stretching from California to Canada, including the Yurok, Tolowa, Squamish, Tillamook, and Quileute peoples. What they found was striking. Nearly the entire Pacific coast seemed to be describing the exact same singular earthquake and tsunami event, generation after generation, through stories of violent shaking, the ocean retreating and then crashing back in, and landslides burying entire villages. These oral histories captured the emotional and physical reality of the disaster beautifully, but they lacked something scientists desperately needed, an exact date. That answer would eventually come from a much stranger source, dead trees. Along the Oregon coastline sits the Niskoan Ghost Forest, a haunting collection of long dead western red cedars standing frozen near the Copalis River, their trunks rising eerily out of salt marsh mud like remnants of a drowned world. For years, researchers assumed rising sea levels had simply poisoned these trees with salt water over time. Then, in 1987, USGS geologist Brian Atwater published a landmark study in the journal Science, revealing that the surrounding land had actually dropped suddenly, subsiding by as much as 2 meters almost instantly, allowing seawater to rush in and kill the forest in one dramatic event rather than a slow process. Buried within the soil, his team also found telltale layers of sand, the unmistakable signature of a powerful tsunami. This proved a massive earthquake had struck the region, but the exact date remained a mystery. Atwater later teamed up with dendrochronologist David Yamaguchi, a scientist who specializes in reading tree rings to reconstruct past climate and environmental events. By comparing the growth rings of living trees nearby with the dead, drowned stumps in the ghost forest, Yamaguchi searched for the precise moment growth had abruptly stopped. He found it. The final ring on the dead trees dated to the year 1699, with follow-up root analysis narrowing the likely window down to the winter, spanning 1699 into 1700. It was close, but scientists still needed an exact date, and that final piece would come from an entirely unexpected place, more than 8,000 kilometers away. Japan sits at the intersection of 4 major tectonic plates, making it one of the most earthquake-prone nations on the planet, recording roughly 1,500 earthquakes every single year. On March 11, 2011, at 2:46 in the afternoon local time, one of the most powerful earthquakes ever measured struck off Japan's coast. A magnitude 9 event centered 72 kilometers east of Tohoku, at a depth of 32 kilometers. The shaking lasted 6 relentless minutes, powerful enough to shift the planet's mass slightly and shorten the length of an Earth day by 1.8 microseconds. What followed was catastrophic. Entire towns were leveled, thousands of lives were lost, and the Fukushima nuclear plant suffered a meltdown that released radioactive material into the surrounding environment. Total damages eventually reached an estimated $235 billion, an amount so large it could purchase 2 major professional sports franchises outright and still leave hundreds of billions to spare. But the earthquake itself was only the opening act. Within minutes, a towering tsunami wave, reaching heights of up to 38 meters in some locations, roared roughly 10 kilometers inland after the seafloor suddenly thrust upward by 16 meters and shifted sideways by 50 meters. Traveling at speeds around 804 kilometers per hour, comparable to a commercial jet, the wave engulfed entire coastal communities in minutes. More than 19,000 people died, the overwhelming majority from drowning. As devastating as that event was, it turned out history had already offered scientists a strange clue decades earlier. Japan has kept remarkably detailed written records of coastal flooding events for centuries, and in 1996, geologist Kenji Satake of the Geological Survey of Japan was combing through historical documents when he came across something deeply strange. The records described widespread flooding, homes swept away, fires, and even a shipwreck, all caused by a powerful wave that struck in the middle of the night, killing roughly 1,000 people. Yet nowhere in the historical record was there any mention of an earthquake preceding it. Japanese scientists eventually nicknamed this mysterious event the orphan tsunami, because it appeared to have no obvious source. Using centuries-old records combined with modern computer modeling, Satake and his colleagues eventually traced the true origin of that mysterious wave, and the answer was almost unbelievable. It had been triggered by a magnitude 9 earthquake that struck roughly 8,000 kilometers away along the Cascadia fault line in North America. The seismic energy released was roughly equivalent to the total energy the entire United States consumes in a month, thrusting the seafloor upward and sending tsunami waves as high as 5 meters racing across the entire Pacific Ocean, all the way to unsuspecting coastal towns in Japan. By combining this Japanese historical data with the tree ring analysis and sediment studies from North America, scientists were finally able to pin down an exact date and time, the night of January 26, 1700, at approximately 9 o'clock local time. A silent rupture beneath the Pacific Ocean simultaneously devastated coastlines on both sides of the world's largest ocean. Over the 326 years since that last catastrophic rupture, pressure has continued building steadily along the Cascadia subduction zone. We know this isn't just theoretical, because scientists are literally watching it happen in real time. In 2021, researchers aboard the vessel Marcus G. Langseth launched an ambitious survey of the Cascadia zone, using 36 air guns to fire seismic pulses down toward the ocean floor and recording their returning echoes using quality 200 underwater hydrophones attached to a 15-kilometer-long floating cable, essentially performing a giant ultrasound scan of the Earth's crust deep beneath the seafloor. Geophysicist Brandon Shuck from the Columbia Climate School led the massive effort to analyze the resulting data. So much data, in fact, that some findings weren't released until April 2026. The wait paid off, producing some of the clearest images of the fault ever captured. Rather than sliding smoothly and uniformly beneath the North American plate as previously assumed, the Juan de Fuca plate appears to be tearing apart chaotically in pieces as it descends, with massive fractured slabs peeling away and sinking further into the mantle. In one region alone, researchers found the plate had shifted downward by a staggering 5 kilometers due to a major tear. Scientists describe this newly discovered pattern as episodic, or piecewise termination, and it represents a genuinely significant shift in our understanding of how these earthquakes might actually behave. If the subducting plate is fracturing and splitting apart as it sinks, that could fundamentally change how stress accumulates and eventually releases along the fault above it, meaning the next rupture might not unfold the way scientists previously modeled it all. So we now know this has happened before. We know roughly when it last happened, and we know pressure is steadily building toward the next one. The remaining question is simple to ask and terrifying to answer: how much time is actually left? To find out, Chris Goldfinger and his team at Oregon State University turned to reading the ocean floor itself, analyzing layers of deep sea sediment for thicker, coarser sand deposits marking past megathrust earthquakes, then using carbon-14 dating to build a timeline stretching back nearly 10,000 years. What emerged from that timeline was unsettling. Over the past 10 millennia, earthquakes measuring magnitude 8.2 or greater have struck this fault somewhere between 41 and 43 separate times. For decades, Scientists assumed these catastrophic events followed a fairly predictable cycle, roughly once every 500 years. But the growing body of geological evidence paints a far messier, far less predictable picture. Current risk models estimate roughly a 37% chance of a magnitude 7.1 or greater earthquake striking within the next 50 years. For the northern segment of the fault, stretching from Seaside, Oregon up to British Columbia, the odds of a magnitude 9 or greater event specifically sit between 10 and 15%. Perhaps most unsettling of all, we have already gone longer without a major rupture than 75% of all known historical intervals over the past 10,000 years, and within the next 50 years, that figure is projected to climb to 85%. By historical standards, this fault is increasingly uncomfortably overdue. If a magnitude 9 or greater earthquake does strike the Cascadia zone, the destruction would begin within seconds. Seismic shock waves would radiate outward from the epicenter at nearly 5 kilometers per second, with the initial shaking lasting several minutes and aftershocks continuing for months afterward. Computer models paint a genuinely apocalyptic scenario. More than 1 million buildings could collapse or be rendered unusable, highways would buckle and twist, bridges would fail, and landslides could tear through entire neighborhoods. Power, cell service, and water systems would likely fail almost immediately, trapping millions of people in the dark, especially if the quake strikes at night. One particularly dangerous side effect predicted for this scenario is called liquefaction, a process where violent shaking overwhelms the friction normally holding soil particles together. As pressure builds in the water trapped between soil grains underground, the ground itself begins behaving like a liquid rather than a solid, capable of swallowing buildings and vehicles whole within moments. Roughly 15% of Seattle sits on ground vulnerable to this effect, and Portland's industrial district is especially susceptible, raising the terrifying possibility of ruptured gas and oil pipelines igniting into catastrophic explosions from a single spark. And that's before the tsunami even arrives. If the earthquake's epicenter lies offshore, coastal communities may have as little as 10 minutes of warning before a towering wave surges inland. Models suggest these waves could reach heights of 24 to 30 meters along parts of the Oregon coast, traveling at speeds around 788 kilometers per hour, comparable in scale to the devastating 2004 tsunami that struck Sumatra and killed 230,000 people. Some low-lying coastal areas could see flooding penetrate as far as 16 kilometers inland, with waves stretching over 500 kilometers in wavelength and gaps between successive waves lasting up to 2 hours, meaning the danger doesn't simply pass after the first wave recedes. The damage wouldn't stop at the immediate coastline either, with models suggesting destructive waves could reach as far away as Hawaii and Japan. According to FEMA's projections, a worst-case scenario could claim nearly 13,000 lives, with tsunami flooding responsible for roughly 70% of all deaths and injuries, another 27,000 people injured, more than 1 million displaced from their homes, and immediate damages exceeding $150 billion. Given stakes this high, scientists and local governments have begun taking serious action. In April 2025, a coalition of earthquake researchers across the Pacific Northwest, working alongside the University of Washington, launched an ambitious initiative called Project M9, focused on improving evacuation infrastructure for roughly 70,000 people currently living within tsunami inundation zones, the low-lying coastal areas most likely to flood. In a worst-case scenario, some communities could see the first wave arrive in under 60 seconds, making traditional evacuation on foot essentially impossible if higher ground sites more than 8 kilometers away. Rather than relying purely on speed, the Shoalwater Bay Indian Tribe took a different approach in 2022, constructing the first purpose-built tsunami vertical evacuation tower in the United States, located in Tokeland, Washington. Standing 15 meters tall, 12 meters wide, and capable of sheltering up to 400 people, the structure is anchored by concrete pilings driven 16 meters into the ground, engineered to withstand an earthquake with roughly a 1 in 25,100 year likelihood, resist liquefaction, and survive up to 3 meters of lateral ground displacement. Currently, only 2 other similar towers exist in the region, with a 4th planned for Westport, Washington by 2027. Experts warn this is far from sufficient, estimating that the coastal communities of Oregon and Washington combined would realistically need around 50 such refuges to provide adequate protection. This design closely mirrors similar towers found throughout Japan, a nation with over a millennium of hard-earned experience adapting to tsunami threats, having endured roughly 143 documented tsunamis since 684 AD, claiming more than 130,000 lives throughout its history. Japan has since developed one of the most sophisticated multi-layered tsunami defense systems on Earth, including vast underground flood control networks, over 400 kilometers of coastal seawalls reaching up to 15 meters in height, and rapid early warning systems capable of alerting the public within minutes. Yet perhaps Japan's most powerful defense isn't concrete or technology at all, it's culture. Generations raised, understanding exactly what to do the moment the ground begins to shake. The Pacific Northwest, by comparison, still has considerable ground to cover. Infrastructure remains uneven, warning systems are comparatively limited, and public awareness varies significantly from community to community. Some Oregon residents have already begun preparing personal 2-week emergency plans, acknowledging the grim reality that after a major Cascadia event, they could realistically be cut off from outside help for up to 2 weeks. Authorities continue urging residents to sign up for official emergency alerts, stay informed through verified channels, and memorize evacuation routes long before they're ever actually needed. For the millions of people living along this stretch of coastline, all of this serves as a sobering reminder that the ground beneath their feet is never truly at rest. Right now, scientists are steadily learning to read the false warning signs, watching it shift, breathe, and tremble through some of the most advanced monitoring technology ever built, and slowly refining our understanding of just how often these catastrophic events tend to recur. But despite every technological advance, the exact moment this fault will finally rupture again remains unknown. What we do know, with unsettling certainty, is that someday the accumulated pressure will finally give way. The ocean floor will lift, the coastline will shake violently, and the Pacific will surge inland once again, just as it did more than 3 centuries ago. The final chapter of this story hasn't been written yet, but somewhere far beneath the waves, it may have already quietly begun.